As long as humans have walked on the face of the earth, we have wondered about the world around us. We have been driven to understand the mysteries of nature and the universe. Throughout recorded history, man has developed theories to explain why things are the way they are, and then designed experiments and built machines to test those theories. Each generation is built on the lessons of their predecessors, and each generation has produced wonders that their ancestors could only have dreamed about. And because the desire for knowledge is part of our nature, we are continuing to challenge the limits of our knowledge. Located in eastern Texas, the superconducting supercollider will be the largest machine ever built for research and experimentation. It will be used to learn more about the basic forces and the elementary particles that make up our universe. The supercollider will lie deep beneath the Texas plains in a tunnel that is 76 kilometers or 54 miles in circumference. Inside the 5-meter-wide tunnel, 2 magnetic rings will be used to guide and focus counter-rotating beams of protons as they are accelerated by radio waves to near the speed of light. The protons will collide head-on with a combined energy of up to 40 trillion electron volts. The collisions will recreate conditions that are thought to have existed only in the first 10 billionth of 1 trillionth of a second after the creation of the universe. For scientists, it will be like looking through a microscope back into time. The supercollider will be the crowning achievement of 20th century physics and a dominant force for the first quarter of the 21st century. The discoveries that the SSC will produce in the future can only be theorized now, but simply the building of the supercollider is already providing valuable results. Under a unique technology transfer program, the American scientific community is forging a partnership with American industry. Working together, they are developing new technology that will help the United States maintain its position as the world's dominant scientific and industrial leader. The heart of the SSC is its system of magnets. There are 3 basic types, and they are the means by which the protons are guided and focused. Just the sheer number of magnets required is an indication of the magnitude of this ambitious project. There will be more than 8,000 dipoles, which are the most common element of the system. They are called dipoles because they have 2 magnetic poles, north and south, just as in an ordinary household magnet, but they are anything but ordinary. Measuring 15 meters or about 50 feet long, they each weigh about 15 tons and operate with 6,500 amps of current. Each dipole will slightly bend the highly energetic proton beam that passes through a stainless steel tube in the center of the magnet. There will be nearly 1,800 quadrupoles, which are about 1/3 the size of the dipoles. They have 4 poles, 2 north and 2 south. Their powerful magnetic fields emanate both horizontally and vertically, focusing the beam and controlling its shape as it passes through the beam tube. And there will be in addition nearly 1,800 spool pieces. About the same size as the quadrupoles, they will contain correction magnets and instrumentation. The first phase of the Magnet Technology Transfer Program is the construction of prototype dipole magnets. Several theoretical and technical barriers had to be overcome in order to design and build these magnets. Each of the nearly 12,000 magnets in the SSC will have to meet rigorous performance standards. To operate, the magnet's interior must be cooled to only 4 degrees Kelvin above absolute zero or 450 degrees below zero Fahrenheit. But the outer surface, only 33 centimeters or 13 inches away, will still be subjected to warm air. To further complicate matters, the protons must pass through a nearly pure vacuum so that they won't collide with air molecules. Imagine trying to construct a 50-millimeter diameter tube, 76 kilometers in circumference, and made out of 12,000 individual segments without an air leak. And perhaps the most demanding requirement of all, they have to be built for a specified and very tight budget. In previous projects, such as the Fermilab's Tevatron, magnets were essentially designed and built by the scientific community. While these projects were large for their time, they were still small enough that each magnet was basically handcrafted. They were built on-site at Fermilab by resident physicists and technicians. But the sheer size of the SSC requires a different approach. At the peak of construction, Fermilab was able to turn out 10 magnets each week. The SSC will require a production rate of 10 magnets each day. Using the technology transfer program, a new way of designing and building the magnets is evolving. Working from a design developed jointly by 3 national laboratories, outside corporate contractors are working alongside the staffs of Fermilab, Brookhaven National Lab, and Lawrence Berkeley Laboratory. They are learning how to construct the new superconducting magnets. The benefits to American companies will be long-lasting. They are reaping valuable knowledge in several new fields, including metallurgy, superconductivity, material science, and cryogenics. The core industrial groups that are working at LBL, BNL, and Fermilab now will go back home and spread the technology throughout their company and beyond to their subcontractors. The technological lead that this will give to our nation's businesses is a tremendous boost in the never-ending struggle to maintain America's edge in the international business world. The expertise developed from constructing the superconducting magnets will be directly applicable to such diverse industries as aerospace, transportation, medicine, manufacturing, communications, power transmission, shipbuilding, and national defense, to name just a few. The benefits to American science are equally impressive. The corporate partners are using their expertise to make the scope of the SSC project manageable and thus affordable. Manufacturing and industrial engineering methods developed in the aerospace and heavy precision manufacturing industries are being applied to the project in order to reduce unit costs and increase operational reliability.
All right, let's
For
take this thing
example,
home.
winding the coils of the magnets has always been a time-consuming, largely manual endeavor. It is the first step of magnet building and one of the most critical. A crew of 3 or 4 well-trained people can wind just 1 coil in about 2 days. 4 coils must be wound for just 1 dipole. The coils are wound from flat cable containing from 30 to 36 fine wires. Each wire consists of about 8,000 individual filaments made of a niobium titanium superconducting alloy. Nearly a half mile of cable is wrapped into a tight, controlled pattern for each coil.
Okay.
This is a painstaking process that could be accurately described as being more of an art than a science.
I like it.
However, once the industrial partners have gained sufficient experience in winding coils and understand the manual art, they will be able to develop an automated process. By applying robotics and computer numerical control techniques, they will design machines that will perform this tedious process quickly and with great precision. Of the tens of thousands of coils that will be wound, each will be identical to the others. After each coil is wound, it is cured and then inspected for mechanical and electrical properties. The process is called sizing and currently takes 2 people at least a day to perform. They need to measure and inspect the coil one small section at a time, up one side and then down the other. It is a monotonous process, yet it requires the utmost dedication to catch any minute flaws that might exist. A single stray sliver of metal, invisible to the naked eye, can cause the entire magnet to fail. Automation has already been applied to the sizing process. Although this prototype machine is still rudimentary, it's yielding valuable lessons about how to scale up the operation while increasing the reliability of measurements. In the technology transfer program, each of the literally thousands of steps in building the dipoles is being carefully scrutinized. Each step is subject to the increases in efficiency and quality that can be expected from large-scale application of precise, modern manufacturing techniques. These prototypes will never see service in the SSC. Their function is to be tested and evaluated and to serve as the bridge in the technology transfer process. They are the forerunners of new equipment and new precision processes that will for the first time make possible the volume manufacture of superconducting magnets, America's magnets of the future. From these prototypes, we are gaining the knowledge that will enable us to build powerful superconducting magnets in high volume with low unit cost and with outstanding quality. For industry, they are the means for transforming scientific theory into industrial technology. For people, mastery of the industrial technology is the first step in creating new products, new jobs, and new opportunities. And it's happening now through the laboratory's technology transfer program, an early demonstration of how the science and technology of the Super Collider will contribute to a better future for all of humankind.